Sequence impedance and sequence network of three-phase load. Sequence impedance definition: the sequence impedance are the impedances offered by the devices or components or circuits for the sequence component of current. The sequence impedance of the network describes the behavior of the system under asymmetrical fault conditions. There are three sequence impedances: positive sequence impedance, negative sequence impedance, and zero sequence impedance. So positive sequence impedance, the impedance offered to the flow of positive sequence currents is known as positive sequence impedance. It is denoted by Z plus. And negative sequence impedance, the impedance offered to the flow of negative sequence current is known as negative sequence impedance. It is denoted as Z minus. And zero sequence impedance, the impedance offered to the flow of zero sequence current is known as zero sequence impedance. It is denoted as Z naught. Consider a three-phase balanced load with impedances Zs at all the phases, and the neutral is grounded through an impedance Zn, and the load is a star connected load with neutral grounded. The line to ground voltages are given as VA, VB, VC, where VA equal to this Zs into IA plus Zn into In. Similarly, VB equal to Zs into IB plus Zn into In. Similarly, VC Zs into IC plus Zn into In. For an unbalanced system, the phase current IA plus IB plus IC, that is equal to the neutral current In. So substitute this condition in the first equation. Instead of In, we are going to substitute IA plus IB plus IC. So the first equation becomes VA equal to Zs IA plus Zn IA plus Zn IB plus Zn IC. Similarly, VB Zs IB plus Zn IA plus Zn IB plus Zn IC. Similarly for VC. And in this equation, the phase voltage equation, you will be having two IA terms. So take IA as common, you will be getting Zs plus Zn, and VB term, two IB terms are there. Here on IB and this is on IB, and Zs plus Zn, take IB as common, and the third equation, take IC as common, you will be getting Zs plus Zn. That is your third equation. And now we are converting that equation into a matrix form. So VA, VB, VC, the phase voltages, that is equal to the Z matrix, coefficient of all the phase currents, and into the phase current IA, IB and IC. This is your fourth equation. And in simplified form or a compact form, this VA, VB, VC, we can represent it as VABC, that is equal to ZABC into IABC. Considering the same equation here, VABC equal to ZABC into IABC, and where this VABC, the phase voltage, equal to the transformation matrix into the symmetrical component of voltage or a sequence voltage V012, where this 012 represent zero sequence, positive sequence and negative sequence. And similarly, IABC equal to transformation matrix into I012, the sequence component of current, symmetrical component of current. Substituting this expression in the fifth equation, we will be getting T into V012 equal to ZABC and into T into I012. Now multiplying by T inverse on both sides. So T inverse into T V012, that is equal to T inverse ZABC T I012. Now, so here the T and T inverse get cancelled, so you will be getting V012, that is a symmetrical component of voltage, that will be equal to T inverse ZABC into T into I012. So this term will be equal to Z012. The product of the transformation matrix inverse ZABC into transformation matrix, that is your Z012. Substituting, will be getting the symmetrical component of voltage. So considering this equation, substituting the transformation matrix inverse, that is 1 by 3, 1, 1, 1, 1 A square, 1 A square A, and the Z matrix, and finally the transformation matrix 1, 1, 1, 1 A square A, 1 A square. By doing the matrix multiplication of these three terms, we will be getting Zs plus 3 Zn, 0, 0, and 0 Zs 0, 0, 0 Zs. Zs plus 3 Zn is your zero sequence impedance, and this Zs is positive sequence and this Zs is negative sequence. This is your sequence impedance of the three-phase load. Now we are going to see the sequence network of a three-phase load. Now, sequence network definition. The single phase equivalent circuit of power system formed using the impedances of any one sequence only is called the sequence network. There are three sequence networks. One is positive sequence network, negative sequence network, and zero sequence network. Positive sequence network for a given power system shows all the paths for the flow of positive sequence current in the system. Negative sequence network for a given power system shows all the paths for the flow of negative sequence current in the system. And zero sequence network for a given power system shows all the paths for the flow of zero sequence currents. The first condition is star connected load grounded through impedance Zn. So for zero sequence network, you have to substitute the zero sequence impedance Z0, that will be equal to Zs plus 3Zn. That is what we derived. It consists of the two terms. One is Zs and 3 times the neutral impedance, 3 into Zn. And the current IA0 in this direction and the voltage is VA0. This is your zero sequence network. And the positive sequence network will be having a positive sequence impedance Zs and IA plus and VA plus. Similarly, negative sequence Zs, IA minus and VA minus. So this is how you need to draw the sequence network for star connected load grounded through impedance Zn. Second case, solidly grounded three-phase load. So there is no impedance, the neutral is directly grounded. So in such case, the zero sequence impedance having only Zs, there is no Zn term, so it is short circuited and it is grounded solidly, and the positive sequence and negative sequence network remains same as the previous case. And third case, ungrounded three-phase load, the neutral is not grounded. In such case, for zero sequence, you need to open these terminals, zero sequence impedance are present and VA0, IA0. Similarly, positive sequence and negative sequence network remains same for this case as well. Next one, the sequence network of delta connected load. So here the zero sequence network can be represented like this. The sequence impedance will be represented as Z0 and the current will be flowing around this loop, that is IAB0. Current IAB0 is flowing in this loop, and there is no zero sequence current flowing in this path. Since it is a delta connected load, so it is open circuited. And the positive sequence and negative sequence network remains the same as the previous case. These are the sequence impedance and sequence network of a three-phase load.